Good morning. In this lecture, let's investigate about diversity in wireless communications. Why diversity is important in wireless communications, or how diversity can improve the performance of, say, our wireless communication system. Before we venture into the actual details, let's consider a simple scenario. Say you have a transmitter and a receiver, and there is a wireless communication link associated between transmitter and say receiver. Okay, this is your wireless channel, or you have a single link between transmitter and receiver. Now what you want is you want to transmit a symbol, say X. I want to transmit a symbol from transmitter towards receiver over this single communication link available, or single wireless link available. Okay, now say unfortunately you're willing to transmit symbol over this communication link, but say unfortunately this communication link is in deep fade. Okay, this communication link is in deep fade. We will understand about this deep fade, what this deep fade is. Generally, when the received power, okay, otherwise we can don't go for receive, like simply say like this. When the symbol's power, okay, if it is less than the variance, the noise variance, okay, if this is the case, then we cannot distinguish our actual symbol from the noise. Yeah, otherwise your symbol power will be well below the noise threshold. If that is the case, you can simply say that your channel, your wireless link or wireless channel is in deep fade. Okay, so therefore, if that is the case, almost there will be no communication, yeah, between transmitter and receiver, because you don't have any other alternative path for this symbol to get transmitted from transmitter to receiver side. So now how do we overcome this problem? So what do we do at this juncture? So one of the possible solutions what we have is, you have a single link. What if I take multiple links between transmitter and receiver? Okay, otherwise, can we introduce multiple links between transmitter and receiver? And if any one link fails, it's not that all links may fail, just together. Say one link, if it fails, other links may work properly. So definitely you can transmit your symbol over these other links. Okay, so you need not worry now if one of the links is in deep fade. Okay, so one of the appropriate things is that we can go for multiple links instead of a single link. Okay, and who is addressing this? So Mr. Diversity is addressing this. So Mr. Diversity is saying that I am here and I will try to overcome this deep fade problem. So Diversity is saying that, so deep fade, now you cannot show your talent. Okay, so I came into the picture now. So now I can overcome the problem of deep fade, like he is assuring us. So Diversity scheme is assuring us that though there is deep fade, so your symbol can take another alternative paths. Okay, so happily your symbols can be received at the receiver side, and that's what. So diversity can overcome the problem associated with deep fade. Okay, so multiple links is nothing but diversity. By having multiple links between transmitter and receiver is nothing but diversity associated between transmitter and receiver, or diversity associated with your wireless communication system. Okay, so You have several types of diversity. Say you have like, what is this? Okay, let me go here. Okay, I think, yeah. Say you have frequency diversity, time diversity, polarization diversity, angle diversity, multi-user diversity, and there are many other types. So we will try to focus today on spatial diversity, or I can say simply space diversity, or you can say antenna diversity. Okay. So antenna diversity. When I say antenna diversity, again, you have like transmit diversity. So transmit diversity, you have receive diversity, and you have, I can also take both diversities. Okay, both transmit and receive diversity we can include. Okay, so for instance, say that you have a, okay, let me take this block. Say I have transmitter, and let me take a receiver like this. Okay, so let me remove this. Let me take a receiver. All right, so okay, yeah, so he is Mr. Transmitter and he is Mr. Receiver. All right, so let's go for transmit diversity. So if, let's take, we have two antennas here, say transmitter antenna 1, transmitter antenna 2, and you have say a single receiver antenna, say R1. Okay, and now what we do here is there is a link, a wireless link between T1 and R1, and also another wireless link or another independent alternative path between transmitter antenna T2 and receiver antenna R1. See, because of two transmitter antennas, I have here two individual links. Okay, say that this is a link 1 and this is link 2. If link 1 is in deep fade and if link 2 works, then you can happily transmit your symbol over this link 2. If link 2 fails, or if link 2 is in deep fade and if link 1 is working properly well, then you can transmit your symbol over link 1. So what if two links fail? Yeah, there may be cases like that. So in general, it's not that all links they fail at once. So, or in general, you can take more number of antennas, say at the transmitter side or at the receiver side or at both transmitter receiver side, so that you can generate more links, or diversity is even more in your wireless communication system. So the chances of successful transmission of symbol will be good, okay, in that situation or in that case for that matter. Now this is, of course, as we have multiple transmitter antennas. So as I have multiple transmitter antennas at the transmitter side, and due to which you have multiple links, so therefore it is called as transmit diversity. Okay, so multiple antennas at transmitter, so therefore it is transmit diversity. And the next one is this. Case 2 is receive diversity. So I have transmitter, and let's take a receiver here. Now, okay, let's take, I have three receiver antennas, say receiver antenna 1, R2, and R3, and I have single transmitter antenna, say T1. Now you have three paths, right? See, from T1 to R1, path 1, T1 to R2, and T1 to R3. So you have three individual paths, wireless paths. So you can transmit your symbol over these three paths if you want. Okay, so now say this is your link 1, link 2, and link 3. Say link 2 is in deep fade. Okay, that means you can't transmit your symbol over link 2. Now you can transmit your symbol over link 1 and or link 3. Okay, so now the probability of successful transmission is good in this case. So as you have multiple receiver antennas, and because of this you got multiple links, so therefore it is called as receive diversity. Now what if I take both transmit and receive diversity thing here? Okay, see, I have transmitter and you have receiver as well. So yeah, let me take, okay, black. Okay, so I have a let me take for simplicity only 2 transmitter antennas and 2 receiver antennas. Okay, so transmitter antenna 1, transmitter antenna 2, receiver antenna 1, receiver antenna 2. So you have total 4 links, right? So now we can show 4 links. Okay, yeah, so from T1 to R1 one link and T1 to R2 another link you have. Okay, similarly I have T2 to R1 one link and T2 to R2 I have another link. So therefore, say this is link 1, this is link 2, this is link 3 and link 4. You have 4 links now. Say if link 4 and link 1 say it is in deep fade, then you can happily make use of link 2 or link 3 to transmit your symbol over those links. Okay, so that's it. So this is how diversity can improve performance of your wireless communication system. Yeah, so obviously, so the main goal of this what you call diversity is that it can overcome the problem or the effect of deep fade. Okay, so whenever you encounter deep fade events, so you can happily think of alternative paths so that your symbol can go over those alternative paths towards your receiver side. Now, okay, let's try to observe this what you call this deep fade problem. Okay, what is the condition for this deep fade? So for that, let's take okay, relay fading channel. Let me take relay fading channel model. Let me take a transmitter and receiver with single antenna each. Okay, let me take this model. I have, say, a transmitter and I have single antenna there. I have a receiver with single antenna. So this is, say, T1, this is, say, R1, and this is the wireless link. Okay, say between T1 and R1. Now we can associate fading coefficient or Rayleigh fading coefficient for this, right? So let me say the fading coefficient generally is complex. Okay, so let me take h is equal to a e to the power of j5. So we are showing this h in polar form. So I have both magnitude as well as phase. Okay, so phi is phase and a is our amplitude of this, say, fading channel. Now, say the transmitted symbol is, let me take, let's say that you are transmitting a symbol x. Okay, so transmitted symbol is x. See, when we say symbol, that means symbol is a group of bits, or you can say it's a bit stream, and it depends upon your digital modulation schemes. If you use BPSK or QPSK or say 8PSK or 16 QAM, 64 to 56 QAM, so on like that. So based on that, how many bits a symbol can carry, that depends upon, of course, your modulation scheme. For example, if I take QPSK can carry two symbols, I mean 2 bits per symbol. If I take BPSK, per symbol, BPSK can carry only one symbol. That means over the same spectrum, in that case, what I can say is that with QPSK, the data rate is double when compared to BPSK. So that's a different story. We will discuss those things in our subsequent lectures. So let's not go into those lines for now. So anyways, transmitted symbol is X. Now say received symbol is Y. Let's say received symbol is Y. All right. And I want, of course, Y to be X. Okay. So if you have a noise free, say in ideal case, you have a noise free environment. So whatever you transmit, I get the same thing. Okay. So that's what, of course, required. Yeah. But in practice, it's impossible, right? In practice, the channel is always noisy. So noise-free channels are highly impossible cases in practice. Anyways, so you have transmitted symbol X and received symbol Y, and this is our channel, or you have single link here, okay? And this channel is H in this case. So therefore, what we can say is that, so you multiply your channel, okay? You multiply with your channel by your transmitted symbol X, and this is again W. You have to add, of course, there will be noise in the environment, so that noise is this W, and now this is what your Y, okay? Your output symbol or your output received power generally write like this, okay? So my this is my receiver symbol, okay? This is my transmitter symbol, and this is our noise. So generally you have we assume like you have white Gaussian noise, mean at 0, and variance, the variance of this, variance means in this case noise power, okay? So variance is equal to sigma square, and of course variance sigma square is nothing but noise power. Yeah, and I always want to expect my received power is well above this noise power. Then only we can distinguish our actual symbol power from noise, right? So otherwise, no. Yeah. So now what we do here is we will try to see the situation or the condition for deep fade event. Now my transmitted symbol's power, let me take like this. Let's say, let me take another color. Let's say transmitted symbols power, I mean that excess power is, say, okay, some P sub T. Okay. Now, what must be the received power? If you receive any signal, the received power in this case is what? I have channel as H and transmitted symbol as X, right? So symbol's power is PT. This symbol's power is PT. And now received power is nothing but, okay, take magnitude of this channel, square it, and multiply by your transmitted symbol power. That is what here in this case PT, okay? Now, what do you have H here? H is a complex quantity, A into e to the power of J5. So I have A e power J5, take its absolute value or magnitude, square it, multiplied by P sub T, transmitted symbols power, and transmitted symbols power is P sub T only, okay? So therefore, this is like A square P sub T. So this is what my received power, okay? Why? How it is a square here? So a e power j5. So e to the power of plus or minus j5, if you take its magnitude, it's always equal to 1, right? So of course that part you know. So received power is a square pt. Now if this received power is less than the variance, or if it is less than sigma square, or if it is less than the noise power, then you have the problem. If the received signal power is less than noise power, that is sigma square, then this is the condition which gives you deep fade event. This is unfortunate, right? So bit error rate is high in this case anyway. So deep fade event. Now I would like to know, like, what is the channel coefficient's value or amplitude of that channel coefficient? What is that is causing this deep fade event? Okay, so for that, what we do is we will try to find out this a square. A square is less than sigma square over p sub t. That means this a square is less than 1 over, you know, symbol power is pt and noise power is sigma square. And see, symbol power or signal power over noise power is what? Signal to noise ratio, right? So that means your a square is less than 1 over SNR, right? Otherwise, your a is less than 1 over square root of this SNR. So what's the meaning of this? So the meaning is this channel coefficient is very poor. That means this quantity, this a, is less than 1 over square root of signal to noise ratio stuff. And so this quantity is very poor. So your channel is in deep fade now. Okay. So to overcome this problem, what we have to do, as we discussed already, you have to you have to take help from this diversity scheme. That means diversity can overcome the problem of deep fade event by introducing more number of paths, yeah, within your wireless communication system or between transmitter and receiver for that matter. All right, let's try to unlock several other concepts or deep fading, I mean this deep fade order, all these things in our subsequent lectures. And especially we'll focus more on this OFDM. Okay, because many asked me like why we use IFFT block, inverse fast Fourier transformation at the transmitter side, and fast Fourier transformation block at the receiver side within OFDM system. So I'll try to make a video on that, and let me try to explain that concept in simple terms. Okay, so that's it for now. So you have deep fade events like this. The condition for deep fade event is this. So to overcome deep fade situations, you will have to go with diversity. So diversity will introduce multiple links or multiple or independent alternative paths. So if some paths are in deep fade, at least other paths can be available, and over those paths you can transmit your say symbols targeting towards your say, receiver side receiver. Now similarly what you have is that you have other types of diversity, say frequency diversity, time diversity, angle diversity, polarization diversity, multi-user diversity, and so on. There are other types of diversity as well. For example, frequency diversity, if you take, let me take a single symbol. Say I have a symbol, and this symbol we transmit over different carrier frequencies. For example, I have, say, carrier frequency 1, another carrier frequency 2, and another carrier frequency 3. Now I transmit this symbol, okay, over this carrier frequency, this symbol again, same symbol over another carrier frequency, again this same symbol over another carrier frequency, and so on. With this, of course, you are producing multiple links. So if some links are in deep fade, at least other links could be success, and you can transmit your symbol. Similarly, time diversity means you are transmitting same symbol over different time slots. When I say different time slots, you have different wireless channel links. So you can transmit your symbols over these channel links. If some, again same story, that is, say I have 3 channel links. If one of the channels is in deep fade, at least other 2 are available for me, so that I can transmit my symbol over any of those 2, or those 2 channels I utilize for symbol transmission otherwise. Okay, so anyways, thank you for now. So again, we will meet with the mathematical insights of this deep fading, okay, concepts or diversity concepts in our subsequent lectures, and I'll do this OFDM lecture as well. Okay, thank you.